Okay, this lesson is about multiple representations of functions, and there are three main representations for functions. It can be, well, there's four. The expression can be said verbally, okay, and that verbal expression can be written as an equation, a table, or a graph. So an example here, verbally, an amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. We can make an equation for that by saying that the profits equals 20 times the number of tickets. We can also make a table for the data that shows how much profit they would make from each number of tickets sold, or we can also graph this. So the same data can be represented in different ways. If you are given a table, if they're giving you the table to work with, you can use that table to find the infinite differences or the ratios, which will let you determine which parent function best describes the function. You can use the table to graph points from the table and to look for a pattern. You can use the table to match the data to the related parent function, or you can also use the table to put that information in your calculator to make a regression to find out the equation there. If you're given the graph, you can look at the graph and identify the parent function, which parent function it comes to. You can use the graph to identify key points. You can use the graph to take points and take those points and make a table from them. So you can make a table from the graph. You can use the graph to find the slope of whether or not it's increasing or decreasing. If you're given an equation, you can make a table of values from that equation. You can take that equation, you can put it in your calculator. You can make a graph, from that equation. And if you're given a verbal description, you can use that verbal description to identify the dependent and independent variables, to make a table, or to sketch a graph of that relationship. So each of the representations of data are helpful to us in different ways. So let's look at an example of this. Here, an investor buys property for that's not right. Okay, in this example, a hotel manager knows that the number of rooms the guest will rent depends on the price. A hotel manager, the hotel's revenue depends on both the price and the number of rooms rented. This table shows the hotel's average nightly revenue based on the number of rooms. Use a graph and an equation to find the price that the manager should charge in order to maximize his profit. So we're given this table. And in this table, they're telling us the price per room and the revenue that he makes for each price. So when we look at this data, when you're giving a table, one of the things we can do is find the difference to tell us which type of parent function this is. So if we find the difference between these revenues, so if we look at the data in the off the chart, and then we find the difference between the two values. Okay, we can find the first difference, and when we find the first difference, we have 1,400, 1,000, and 600. Okay, since the first differences are not the same, that means the function is not linear. Let's go again finding the differences until we see that the function is the same. So if we find the differences for the next ones, the second differences, that was the first difference. If we find the second differences, we can see that the second differences are the same. They're both 400. So since the second differences are the same, 400, that lets us know that this function is quadratic. So quadratic means the second differences are the same, and if the first differences had been the same, that would have been linear. So we know this is going to be a curve, a parabola. Let's go ahead and graph these points. So just looking at this graph here, if I take these points and I graph them, I can see that these three red points here are what the graph is. When that happens, can I use this graph to answer my equation? Well, they want me to find the maximum. And it looks like the maximum for this, after I graph it and after I sketch it in, is actually past where the red dots are. So it looks like the maximum is over here. And I would have to estimate from this graph where the maximum is. So instead of doing that, I'd like to make an equation so I can find the exact point of where the maximum is. Okay, so I could estimate it though. It looks like it's a little less than 25,000, right? So, okay. So let's go ahead and put this data into our calculator. So what you're going to do is you're going to go to your calculator and you're going to enter in this data under stats. Okay, you're going to put this in the table, put this data in, and then we're going to do a quadratic regression. And when we do so, this is the function that we're going to get. Okay, we get this function. Okay, so now I'm going to take this function that I got from using the quadratic regression on my calculator, and we're going to graph it on our calculator. And when we do, you might want to change your window settings so that you can see it better. And those are the window settings I used. And after we graph it, we can also use our calculator feature to find the maximum point. And the maximum point ends up being 110. So he should sell 110 rooms to maximize his profit, which will give him a profit of $24,200. So, okay. So, we're given a table. We can use that table to make a graph. We can also take the information from the table and put it in our calculator and find the function, so find the equation. We can use that equation to find the maximum point, the maximum value, to answer the question. So we were able to use multiple representations of the same data. Let's look at another example. Ticket sales were good until the massive power outage happened on Saturday. It was not repaired until late Sunday. Let's see if we can sketch a graph to represent this situation. Okay. Okay, so we know that ticket sales were good. So we need a high ticket sale number to start off with. So we need a point that's high for Friday. And we don't tell us exactly how much money is sold, but we can just make a high estimate. Like we'll put a point high. Oops. Okay, and then we're on Saturday, it's going to go, on Saturday, like partway through the day, is when the outage happens. So ticket sales are probably moving in a good direction on Saturday, but then, okay, so ticket sales on Saturday were probably moving along just fine until it broke. So they had some sales on Saturday, but then, so it needs to come down to come to Saturday. And then on Sunday, it wasn't repaired until late Sunday. So that means that most of the time Sunday, they weren't getting any money until the very end when they started to make just a little bit. But they probably made less than Saturday, right? And then Sunday it was repaired, and then Monday it starts working again. So Monday's going to be going back up. So even though they didn't give us exact numbers, we can make a sketch, given the verbal argument, we can make a sketch of the graph of how the function might look. Okay, just as long as it shows that it's decreasing until Sunday and then starts increasing again. Okay, Jane is rowing across a 80-meter wide river at a rate of 3 meters per second. Create a table, an equation, and a graph that show the distance that she has remaining before she reaches the other side. So at 0 time, she has a distance of 80 meters wide, the whole river. Then she's crossing at a rate of 3 meters per second. So that means that for 1 second, each second that goes by, the distance is going to decrease by 3. 80 to 77 goes down 3, and then 77 to 74 goes down 3. It's going down by 3. So that means that the first differences here are all 3, and that we can expect a linear function. We can take these points and graph them to make a table. So we can put these points, we're going to have 0 up here at 80, and over here at 4, let's go ahead and graph these points. Okay. Okay, so here's a graph of our situation here. Okay, and I've graphed these same points off of here. So here at 1 would be at 77, and then at 2, this is 3 right here. So 3 is 71, just above 70. And then I just kind of connect those points to draw the whole line. Okay, so we can use this line and we can write the equation for this line. Looks like the y-intercept of the line, where it crosses the y-axis, is 80. And we know our slope is going down 3, so we have a slope of negative 3. And that means our equation is the d equals 80 minus 3t. When does she reach the shore? She reaches the shore over here where it touches the axis at. Um, yeah.